We have already seen Carathéodory extension theorem, and in this brief video lecture we use it to establish existence of the Lebesgue measure and Lebesgue Stieltjes measures. So we start with the Lebesgue measure. It is a unique measure, and then Lebesgue Stieltjes measures. There are many of them. They are parametrized by a cumulative function f, and discuss their relation to well-known to probabilists distribution functions. We start talking about the Lebesgue measure. We're stating the same theorem for the fourth time already. It says on the sample space being that of real numbers and the sigma algebra being that of Borel sets, there exists a unique measure M on this sample space with this sigma algebra that assigns to each interval its length. And that unique measure is called the Lebesgue measure. Recall from the previous lecture what is Carathéodory extension theorem and what it says. It says if we have an algebra of sets on our sample space omega and a premeasure on this pair, the omega, the sample space, and the algebra of subsets, then this measure mu can be extended to a measure on the sigma algebra generated by this algebra A. And moreover, if the extension is sigma finite, or if one of the extensions is sigma finite, then it is the unique such extension. From the theorem, there is one concept here which may require refreshing our memories. What is a premeasure? And a premeasure is, the definition is a bit long, but it's a very mild requirement which we make, is we have a function that assigns non-negative extended numbers to sets in a certain class, that class having the structure of an algebra, assuming it is finitely additive. Finitely additive means the measure of a finite union of disjoint sets is the sum of the measures of those sets, but not necessarily infinite unions. We can't ask such a function, a finitely additive measure, to be a sigma additive because it's defined on an algebra. And on an algebra, maybe we cannot talk about the accountable union of sets on that algebra. Maybe it's not an element of the algebra. So we make this mild requirement that in case the union of accountably many disjoint sets in the algebra happen to be in the algebra, only in that case you require that then the measure of this union is the sum of the measures of each term in the sequence. Recall the definition also of the algebra of left open, right closed intervals. In this algebra we can take complement, we can also take union. So it is an algebra, and on this algebra we can define the free measure of intervals that we call M as simply the sum of the lengths of all intervals composing a set A for every set A that can be written as disjoint unions of intervals. Maybe a set A can be written in more than one way as disjoint unions of intervals, but this will give the same result. You can see more details in the lecture notes. And now here's a big lemma. We will omit the proof of this lemma. It is not that hard, but it will take at least another video lecture just to make the proof. It says this function defined this way, it is indeed a premeasure. And now to summarize, we have defined a premeasure on the algebra of left open, right closed intervals on the real line. With a premeasure, we can use Carathéodory extension theorem because it only requires a premeasure to say it can be extended to a sigma additive measure on the Borel sets, because these are the sets that contain the smallest sigma algebra that contains the algebra of left open, right closed intervals. And the measure is indeed sigma finite, because we can take larger and larger intervals of this form, left open, right closed. They all have finite measure, but as we make them larger and larger, in the end, we get the entire real line. So we have accomplished the proof of this theorem, existence and uniqueness of Lebesgue measure. We had done uniqueness in the previous video lecture, and now we are finishing the proof of existence using the Carathéodory extension theorem.